Okay, let's have examples on fluid pressure on plane surfaces. And later we'll have examples on fluid pressure on curved surfaces. So here we go. First example. For problem 1, compute the force on the side of the tank due to water pressure, the location of this force from the centroid of the area of the side of the tank, and the horizontal force P required to hold the swinging side from opening if this swinging side is a rectangular plate 2 meters into the board or into the screen. Letter B, circular plate 3 meters in diameter. Letter C, isosceles triangle with apex on the bottom portion and is 2 meters across its base. And letter D, parabolic with vertex on the bottom and 2 meters across its base. So this is the figure, and based on the figure, the height of the tank is 3 meters and it is free to swing outward because of water pressure, but it is prevented by this horizontal force P. So for the force, it is, because this is simple, we will have two ways of computing F, two ways in computing E, and two ways of computing P. The first one is by using the formula, specific weight barred H area, and the second one is by computing F, the moment of F about the hinge by integration. So first, let's draw the figure, 2 meters by 3 meters rectangular gate or plate. Let's have this imaginary surface because anyway, barred H is measured from the water surface vertically down to the centroid. So in general, this is the location of the centroid, CG. Its distance from the imaginary water surface or from the water surface is denoted by barred H, and barred H is 4 plus 1.5. So at CP acts the force, and the distance of the centroid of the rectangular plate from hinge A is denoted by H sub G, and H sub G is 1.5. In this case, distance between CG and CP is E. So summation moment about A equals 0. So F times quantity Hg plus E, where Hg is 1.5 in this case, equals P times 3. So our working equation for P is F quantity Hg plus E over 3. So we only need F and E. So for F, we have specific weight barred H area because this is water. 9.81 barred H, as I said, is 4 plus 1.5, so 5.5. And the area is 2 times 3 or 6. So F therefore is equal to 323.73 kilonewtons. Now for E, we have I sub Cg over area barred H because the gate is vertical. So I sub Cg, sine of 90 degrees or 1 over area barred H. I sub Cg is BH cubed over 12 for rectangular area, and area is BH times barred H. So simplifying, this is H square over 12 barred H, where H is the height of the rectangle. So substitute 3 square over 12 times 5.5 or 4 plus 1.5. So solving for E is 0.1364 meters in decimal, 3 over 22 I think in fraction. Then having known E, substitute in this equation, P equals 323.73 times 1.5 plus E over 3. So P is 176.58 kilonewtons. That's the answer for P. Now by integration, so we consider a strip, horizontal strip. It is where the pressure, constant pressure is acting. So we have this dimension y dy. So this is df, and df is gamma or 9.81. Then distance of centroid to the imaginary surface is h or y in general, and that is 7 minus y because we denoted this by y. the total depth up to the bottom B is 7, 4 plus 3, that is 3. So 7 minus y, this is 3 minus y, and that's 7 minus y. So differential force equals gamma 9.1, 7 minus y, distance of centroid to liquid surface, or distance from this horizontal strip to the liquid surface. The pressure is uniform over that area, differential area. And differential area is 2 meters times dy, the area, differential area of the strip. So using your calculator or by manually evaluating the integral, it will give us the same answer in decimal form, 323.73 kilonewtons. If you have your iTech calculator, or you can evaluate this manually. Now for the moment of this force about the hinge, that's also the moment of dF about the hinge. So F times 1.5 plus E, the moment of the force about the hinge is H sub G times E, H sub G plus E, that's the moment arm of F, is equal to integral from 0 to 3 of the moment of differential force is dF times moment arm 3 minus y. So 3 minus y, moment arm of dF, and this is differential F, which we just copy from here. So using your calculator, substitute the value of F, which is 323.73 times quantity 1.5 plus E. The right side using your calculator, or you evaluate that manually, is 529.74. In other words, this value of FHG plus E is 529.74. So the value of P is 529.74 divided by 3. But in solving for E from this equation, E is 529.74 divided by 323.73, then minus 1.5. So E is 0.1364 meters as in the original answer. And finally, P is 529.74. That's the value in the numerator here, divided by 3. So P is 176.58 kilonewtons. So that's it for this case. I presented it into two ways so that you will have two ways also to analyze this problem. For letter B, circular plate 3 meters in diameter. So we will again solve this. So that's the imaginary surface. Centroid is the same. So it's 4 plus 1.5. Then it only matters with the E and the area. So this strip is prepared for the second part of the solution. So same designation. So we'll call that y, then dy. Distance of df from the hinge is 3 minus y. So that's df. That's 3 minus y, and this distance is 7 minus y as before. So f is 9.81. Barred h is 4 plus 1.5. Same. CG, location from the imaginary liquid surface or from the water surface to the centroid of a circle, it's the same, 5.5. Then area of circle, pi, radius square, 1.5 square. So F is 381.39 kilonewtons. Next for E, E is I sub CG over area barred H. So I sub CG of circle is pi over 4, r to the fourth, divided by area pi r square. Then barred H is barred H. So simplifying, that's r square over 4 barred H. Substitute the value of r, which is 1.5 for the circle, 1.5 square over 4 times 5.5. So E is equal to 0.1023 meters. Then for P, so the formula was this. We derived this in the preceding slide. Substitute the value of F, 381.39 times 1.5 plus 0.1023 over 3. So P is 203.7 kilonewtons. Then by integration, so let's have this triangle here. This is y minus 1.5. The radius is 1.5, and let's call that x. The total length of the strip, take note, is 2x. The thickness is still dy. So x squared equals 1.5 square minus quantity 1 y minus 1.5 square. if we simplify this, x squared is 3y minus y squared. So therefore, x squared is 3y minus y squared. Therefore, x is square root of 3y minus y squared. So that's the value of x. Then differential f is gamma 9.81, distance to the horizontal strip 7 minus y. Then the area, differential area is 2x dy. So this is 2, this is x dy. Then integrating using your high-tech calculator, 19.62, quantity 7 minus y, square root of 3y minus y squared dy from 0 to 3. So this is a bit difficult integration. So if you have your high-tech calculator, then it will give you the same result, 381.39 kilonewtons. Then let's solve for the moment of f about the hinge, which is also the integral of df times 3 minus y. So f times 1.5 plus e equals integral from 0 to 3 of 3 minus y, then differential f 19.62, 7 minus y, square root of 3y minus y squared dy. So using your high-tech calculator again, substitute the value of f, then we'll have the right side 611.083. So in other words, the whole value here is 611.083 kilonewton meter. So to solve for E from this equation, 611.083 divided by 381.39 minus 1.5. So solving for E is 0.1023 meters as equal to that. This is the same as that. Then for P, so 611.083 divided by 3, because that's the value of this numerator here. So P is equal to 203.7 kilonewton meter. Then for letter C, we have an isosceles triangle, 2 meters across the base at the top, then the apex is on the bottom. So let's call that CG. Then this HG here is 1/3 of 3, so 1 meter. Then this is CP, distance is still E. Then that's barred H, which is equal to 4 plus 1, so 5 meters, barred H this time. So F is 9.81, 4 plus 1, this is barred H. Then area 1/2 of 2 times 3, which is 3. So F is 147.15 kilonewtons by our manual calculations. Then for E, we have I sub CG over area barred H, where barred H is already found, 5 meters. I sub CG is BH cubed over 36, and area is 1/2 BH, and barred H is, let's just call it barred H. So simplifying this equation, we have h squared over 18 barred h for triangular section. So substitute 3 squared over 18 times 5, then E is equal to 0.1. So substitute in this equation here, P is equal to F 147.15 times 1 plus 0.1 over 3. So P is 53.995 kilonewtons. By integration, let's have a strip. Let's call the length of the strip as x. The thickness is still dy. You just look at that projection. So y as to x equals 3 as to 2. So that means x is 2/3 of y. And so differential f equals 9.81 times 7 minus y times differential area of the strip is x dy, or 2/3 of y dy. So using your calculator, or you can evaluate this easily manually by power formula. So f is integral 0 to 3 of 9.81 times 2/3 is 6.54, then 7 minus y times y dy. It will give us the same results of 147.15 kilonewtons. Then for the moment of F about the hinge, so F times 1 meter plus E is equal to integral of differential force times 3 minus y, or 3 minus y, integral 0 to 3 of 3 minus y times differential force, which is 6.54 7 minus y times y dy. That's the expression for df from this expression here. So we can integrate this manually, but we ran out of space, so I'll just give you the answer, or use your high-tech calculator there. F is 147.15 times 1 plus E equals, the right side is 161.865. So again, the whole value here is 161.865. So E is 161.865 divided by 147.15 minus 1, and will give us 0.1 meter as before, while P is equal to 161.865 divided by 3. So you just replace this by 161.865. So solving for P is 53.995 kilonewton. So this is the advantage of uh, directly evaluating the integral if you cannot remember moment of inertia of these areas here, or you cannot remember the location of the centroids. So that's the advantage if you also have an high-tech calculator, especially if the integral is challenging to evaluate, like for the circle here. So that's it for this case. Then for the last part, we have a parabolic segment or parabolic arc, parabolic gate. The vertex is at the bottom as specified in the problem, then 2 meters across the top. So this time, let's assume that we do not know the location of the centroid, so you can locate that actually by integration, but for the purpose of directly applying the formula, the location of the centroid, the parabola, is from the base 2/5 of the height, which is 3, and from the vertex 3/5 of the height, which is 3/5 of 3. So that's CG, and this is CP. At CP acts F, and at CG, location of CG is again 2/5 of 3. HG is 2/5 of 3. And that's barred H, which is equal to 4 plus 2/5 of 3. So 5.2. HG is 1.2. And we will have a strip in preparation for the integration later. So let's again call that Y. This acts differential F over this differential area here. This is 3 minus Y. And the distance of every element of this horizontal strip to the imaginary surface is 7. 4 plus 3 is 7, then minus Y. So letter D, F is 9.81. 4 plus 2/5 of 3, that's HG. So barred H is 4 plus 2/5 of 3. The area of parabola is 2/3 base times height. So 2/3 of 2 times 3. So solving for F, it is 204.048 kilonewtons. Next, for E, it is equal to I sub CG over area barred H. So assuming we do not know the moment of inertia of a parabola, so let's derive it now. So Ix, imagine that the x-axis is a horizontal line through the vertex. So the distance from the x-axis to every element of the horizontal strip is y, it is constant. And the formula for moment of inertia of area is integral of constant distance square y square dA, where dA is x times dy. So y square dA x dy. Now, by squared property of parabola, y as to x square equals 3 as to 2 square, or in general, h as to b square. So that means that y is h, or x is b over square root of h square root of y. So b over square root of h times square root of y. That's the value of x in this integral here. So Ix equals integral from 0 to h. Let's derive first the moment of inertia of parabola. So b over square root of h, although it was 18 over 175 bh cubed, the formula. Let's show it now. So y square, b over x is b over square root of h, then square root of y dy, then we have y square there. So let's copy. This is y to the 5 halves. The integral is b over square root of h copy, then y to the 7 halves over 7 halves from 0 to h. So simplifying this integral, ix is 2 over 7 bh cubed. So knowing that ix is 2 over 7 bh cubed, and the distance between the x-axis through the vertex and the centroid is 3/5 of h. So by transfer formula, 2 over 7 bh cubed equals I sub cgx plus area of parabola 2/3 bh, distance 3/5 of h quantity square. So since 2 over 7 bh cubed is similar term as this term here in the right side, so 2 over 7 minus 2/3 of 3/5 quantity square, it will give us I sub cgx 8 over 175, sorry, 8 over 175 bh cubed. So having known I sub cgx, we can now compute E. IE is 8 over 175 bh cubed divided by area 2/3 bh times barred h. So E for parabolic area is 12 h square over 175 barred h. So substituting 12 times 3 square over 175 times barred h is 5.2 or 4 plus 1.2. Hg is 1.2. This one, 2/5 of 3 is 1.2. So E is equal to 0.1187 meter. Then for P, so P is F 1.2 plus E times quantity 1.2 plus E divided by 3. So P is 89.692 kilonewtons. For the integration part, so dF is equal to gamma 9.81 of water. Then distance barred h is 7 minus y. Then area is, barred h is 5 for the integration portion. dF is 9.81, quantity 7 minus y, then differential area is x dy. So dF is 9.81, 7 minus y, then x dy. Substituting the value of x, which is b over square root of h, which is b over square root of 3, then square root of y. So f is integral 0 to 3 of 9.81, 7 minus y times 2 over square root of 3, square root of y, dy from 0 to 3. So integrating using your calculator or by manual integration, so 2 times 9.81 is 19.62 divided by square root of 3, quantity 7 minus y, square root of y dy. So solving for f, 204.048, which is the same as that. Then for the moment of F about the hinge, which is F times 1.2 plus E, that's also equal to the integral of dF times 3 minus y. So F times 1.2 plus E equals integral of dF. This is the moment arm of dF, 3 minus y, and this is dF. Let's just copy 19.62 over square root of 3, 7 minus y, quantity times square root of y dy. So using your calculator again and substituting the value of f, 204.048 1 times quantity 1.2 plus e is 269.074. So that means the entire value at the right side is 269.074. This is the moment of the hydrostatic force F about the hinge. Then the value of B is, we simply divide that value by 3. But solving for E, 269.074 divided by 204.048 minus 1.2. So E is 0.1187 meter. Then finally for P, 269.074 divided by 3. So P is equal to 89.691 kilonewtons, which is practically equal to this value here. So that's all for the solution of this problem. This is the basic one, and I hope that you were able to follow the solutions.